So last time I think we have talked about the history of gas separation membranes, and we knew that Monsanto first developed this the hollow fiber system, but they made first a polysulfone membrane, but there is a defect, so they coat these defects with the polydimethylsiloxane or silicone rubber with a very thin layer on top of this polysulfone, so that they plugged these defects, which will result in the recovery of their separation performances. So this was the development of the commercialization of gas separation membranes. And later on, you can make the porous membrane support as a support, and you coat the second layer as a selective layer, which is a little different from the previous cases. The first invention was done by the dense layer. They intended to have the dense layer only, but on the surface, but they could not make the dense layer because of the defects, intrinsic defects of the polysulfone, so that they coat the PDMS and plugged those defects. But later on, you can make the two-layer systems. The first layer will be the support layer, and the second layer will be the selective layer. So this is the concept of the dual-layer membrane or two-layer membranes. If this is the flash membrane, flash it, then you can say that this is the two-layer composite membrane. Or if you can make the hollow fiber with the two-layer systems, the one layer is a kind of support, and second layer is coated with the selective layer. So this is what we call the dual-layer hollow fiber systems. Anyway, this is the very convenient concept, but first invented by the people at the Monsanto, okay? Particularly Hennison Tripathi. And I think I have distributed the PDF files of the science articles already. So I think we also talked about the gas separation membrane systems for nitrogen production. Right? Now we talked about the air separation systems, where the air containing 79% nitrogen is fed into the membrane, and instead of using the oxygen, which was enriched or permeated through the membrane containing 70% nitrogen, we rather use the 99% nitrogen as a retentate. Okay? So 99% nitrogen could be produced by one-stage membrane process, two-stage or three-stage, whatever you call. But anyway, you can have a relative membrane area, but you have to think about the compression forces. Now, I didn't have a time to describe you about this table. And it says that this is the nitrogen production, or nitrogen, the feed rate, whereas in the y-axis you have a nitrogen purity, okay? And in some areas we have different processes. The membrane is defined right in here in this circle, and you can see the cryogenic pressure swing adsorption process, liquid process, cylinder process, stuff like that. This means that there are several processes other than membranes, like a PSA or a cryogenic or liquid, with a different range of feed flow rate, as well as the concentration of the nitrogen. Now you can see the same. We can have the same or similar type of the curves just by changing the gas types from nitrogen to oxygen, or maybe CO2 or whatever. You can have in other words, membrane process is not the universal process. Okay? If you want the same concentration of the nitrogen, such as 99% or 98%, but feed rate is right in this range, yes, membrane is the optimum process for your production of nitrogen. However, if you have a large amount of feed, okay, to treat, such as 10,000 10 million tons of SCF, then cryogenic might be the best process. So depending upon the feed flow rate or the gas that you have to treat, okay, versus the concentration of your the retentate, you have to select the right process. Okay, so in other words, although we are talking about the membrane process is not the ultimate process for nitrogen and other gas for the production. The Monsanto first produced this hollow fiber membrane, and they can make the modules. I showed you last time the small module, but you can extend that. The typical module is, excuse me, is encapsulated with the tube, aluminum tubes or metal tubes, so that you see the largest size of the membrane so far that I have seen is maybe about 5 meter long and about maybe 50 centimeter in diameter. So that's a huge, and you have a huge the number of membrane area inside of this the module. Okay? It's been installed already in the petrochemical industry to remove the hydrogen, from their gases, or to remove the ammonia. Actually, this is the hydrogen production, the petrochemical production, refineries. You can see the first trial, the market for them is to use these membranes for hydrogen production. Even in our the Ulsan petrochemical industry, the SK Petrochemical, they installed the similar the membrane units back in 1986, 87. You see the first production of this Monsanto was 81, 82, and you see SK Chemical adopted this system, right after their the membrane production. So although this is not a consumer product, this is an industrial product, so that you do not know the exact sites for the installation, but in fact there are many of those sites even in Korea as well. This is the generation evolution of the membranes so far. We have already talked about the outer membrane, okay, history of the outer membrane. You see the water versus the hydrated ions, sodium or the chlorides or any other the ions have a difference in size, so you can separate this water versus the hydrated ions using reverse osmosis membrane, using desalination process. The membrane module looks something like this. This is also like a tube, and usually this is the spiral wound module. Spiral wound module was installed in series, and it's packed just like a factory or inventories, and you can extend this the membranes in treating the large amount of the water. Okay? Even today, we have 34 billion tons or billion liters of the water, seawater is treated by desalination units. Before this outer membrane, we knew that, I haven't talked about this at all, but we knew that membrane filtration and ultrafiltration, those membranes were already produced. Okay? The Emicon cell, the company called Emicon was already found before the outer membrane production, and it's been used already in that area. And the gentleman called the Alan Michaels, who was at the time the professor at MIT at Chemical Engineering Department, he found a company called Emicon. It's a startup company, and they already produced this Emicon cell. Still we are using this Emicon cell in the laboratory, But anyway, the Amicon company was later sold to other companies, but the Amicon was the first company. And that's what we call the generation 1 membrane. And this is what we call the generation 2. This is a new progress. And the gas separation membrane could be generation 3 because you see this difference in the size is about twice of 100% difference in the size of this the separating molecules. But you see this, the difference in the size between the hydrogen, which is about 2.9 Armstrong, to about methane is about 3.8 Armstrong. So you only have a 1 Armstrong difference between the small gas molecules. I have already told you that the size of the kinetic diameter of oxygen is about 3.46 Armstrong, and the nitrogen is about 3.64. So you only have a 1.18 Armstrong, which is about 5% difference between the oxygen and nitrogen. So in terms of the kinetic diameter or the size of the gas molecules, this gas separation is much more difficult than RO membrane or MF and UF. So we call this as generation 3. What about generation 4 or membrane 2.0? Right? You can make the membrane 3.0, or you can make a membrane 4.0 if you have any breakthrough in the membrane materials. Okay. Anyway, we are expecting to have a generation 4 or the membrane 2.0. That could be a challenge, and what it is that we already have a generation 3 membrane is staying over here. We have cheap material made of polysulfone or cellulose acetate, but performance-wise, yes, we need much more improvements. So far in the literatures, we can find many materials such as inorganic materials versus the organic material. We can have the material or membrane C, which is very expensive, but have a very high performance. Okay? Because of the cost, although it has a very high performance, our industries are reluctant to use this C type of membranes. And still, we need some more time to develop this the C membrane in commercialization. However, if there is any membrane which has a high performance, not as high as C, but much higher than A, but cost-wise, if you have not many difference, although it's a little expensive, then B could be your choice for the development. So this is what we call the membrane 2.0. Usually, you can see a lot of, in many cases, we have selectivity versus the permeability. Permeability is the intrinsic property of the membrane material, and alpha is also the intrinsic property of the membrane materials. So in order to evaluate your membrane performance in terms of transfer properties, we usually plot this, the permeability versus the selectivity plots. In many materials lie below this yellow line, so that we need a membrane material with a high permeability as well as the selectivity. Now, permeability is determined by, as I told you, membrane material, but if you have a flexibility or free volumes or low graduation temperature, then permeability is high, but the selectivity is low. If you are talking about the rubbery material, usually those materials are rubbery materials. Okay? If you have a flexible and high free volume materials. If you're talking about the glassy polymers have a low mobility, so that it's not mobile, and usually the free volume is quite low. Therefore, the selectivity is high, but the permeability is low. So glassy polymer versus the rubbery polymer lies below this line, but we need the material with this right-hand side in order to make this membrane B or C. So this is the membrane challenge, and it's been already recognized for the last 2 decades. So a lot of people are working on the material development with high performance lying in this region, which is called the upper bound curve, above this upper bound curve. Of course, we have to think about the cost as well. So membrane 2.0, if you have a membrane 2.0, then permeability and the selectivity should be much more important. And there has been several materials with the within the category of membrane B, and the B could be something like TL membrane that we will be talking about, or the membrane with the hybrid systems, hybrid between the commercial polymers falling into category A, combining with the zeolites falling into C, or carbon membrane, so that you mix those inorganics into organic and make it the hybrid systems to improve your performance, but of course your cost will be a little bit higher. So hybrid system, or TL membrane, or PIM membrane, or whatever the membrane that will be falling into these BTEC categories. So we will be talking about the membrane 2.0 later on as well. So ideal membrane 2.0 for high CO2 natural gas cleanup could be the TL membrane that we will be also talking in more details, or cross-linked polymer systems. If you cross-link them, you can improve your performance, but cost-wise, this is not a big problem. So by just taking the cross-linking strategy, you can improve the performance. Okay? You can make the hollow fiber. You can make a module as well. Even today, the membrane cost is less than $20 per square meter for gas separation membranes. But although the membrane material cost will be increased, I think membrane module cost will not be that much increase, in that case. And in the membrane module cost over the system of the full membrane system, such as the system that I'm talking about, the full system cost, among the full system cost, membrane cost or membrane system cost is not that high. Okay? Usually, it's only less than 10% or so. So although membrane material cost will be increased here, the total cost does not increase much. I have elaborated the gas molecules. We have been talking about the small gas molecules in the upper hand side, but we can have little larger size molecules, like ranging from 4 Armstrong to about 5 Armstrong. We can have the aromatic components. The kinetic diameter size will be around 5.5 to about 6.5 Armstrongs. So you see the kinetic diameter size, the size of the molecule will be increasing. And in that case, of course, you need to consider the size of your membrane to separate those molecules, as well as a thermodynamic factor, which is sorption or solubility between the polymer or the membrane material, along with these separating molecules. Okay, this slide shows the history of membrane technology in Korea that I have elaborated a little bit. Okay? After the development of membrane back in the 1970s, in Ulsan petrochemical complex, there was the first electrodialysis membrane plant built in Korea. There was, although I have not seen this unit, I looked at through the literature, and because we had the Korean War in 1950, in early 1950, everything was destroyed, nothing, particularly in the industrial sector, and we rebuilt this unit starting from 65, and we built the petrochemical complex in Ulsan, and Ulsan is located close to Busan, as you know, in the southern part. And President Park at the time built the highway first from Seoul to Busan. This is what we call the Gyeongbu line, the first highway, and the second, the emphasis from this government was putting it into the making the complexes, the heavy industry complex, particularly in Ulsan area. In the Ulsan, there are petrochemical complex as well as the ship building industries there and automobile industries there. And those industries in Ulsan is growing, I guess, right now and globally. And you see the petrochemical industry is developing in that at the time. Now in 80s, the first reverse osmosis plant was built by Gukdong Petrochemical Company in 87. But in 85, even in 85, the Monsanto prism separator was installed to recover the hydrogen gas, as I mentioned, in SK Chemical. And POSCO started the pilot test, the NF and UF and others. And there are other water treatment, particularly ultrafiltration membrane units were installed in the Kia Motor Company. They use a lot of water to coat the outer shell of the automobiles, right? Like a painting. But they use electroplating technology to coat their automobiles, and they use a lot of waters. And they have to treat those contaminated water from the motor company. Right now, Kia was combined with the Hyundai, so this is the Hyundai company. Anyway, the ultrafiltration units are installed right now in every factory of the manufacturing of the automobiles. Right? So you can see membrane units were spreading out in the case. So industry installed the membranes that was developed from outside of Korea at the time, about 30 years ago. And later, I came to Hanyang University in 88, and I knew that starting from at that time, which is about 25, 26 years ago, the government realized that the importance of the R&D funding. Okay? Now, before these 1980s, I think there is not much R&D funding and not much research going on during that time. But I knew that they have started the active R&D funding even on membrane technologies. So I was quite lucky to have the opportunities to do the research in many aspects of membranes. Okay, I put this NRL here, National Research Laboratory Program. They have started the first NRL program in 1999. I was lucky to have this NRL program for the first year, and we have been funded for about 5 years on the membrane laboratory program, and this was extended to a KCLC program so far. So we have been funded for more than 15 years about this membrane. Right now, the funding size per annual funding size will be around up to about I would say $1.5 million per year. Okay? That's a huge project. Anyway, so we were quite lucky to be funded from this program. There are many other programs. You can see, during the 90s, I think there's a lot of programs, and Professor Kang in upstairs, he was quite lucky to have this, I guess, creative research initiative program, starting from '96 or so. And we were okay. I think this is the facility transfer membrane the program at KIST. He was at KIST at the time, but we scouted him in 2005 to Hanyang University. I was lucky to have also the collaborative program with UNSW on submerged membrane bioreactor systems with Professor Tony Fain. But Tony Fain moved to Singapore after retirement at the UNSW, but he's still active, Professor Tony Fain. What we have done on the submerged type membrane bioreactor is that we have developed the membranes for membrane bioreactor, and SK Industry at the time, SK Engineering was doing the pilot testing for the wastewater from the food industry. So what we have done was that we put the membrane modules into the membrane bioreactor, and this was installed in Umsong area in Chungcheongbuk-do area. The factory, the company called the Chodang Dubu. Okay, there is a tofu company, and they, because of the food processing needs a lot of water, so they need to treat the wastewater from their factory, and we installed our membrane bioreactor system there, and we operated about 6 months. Perhaps later on, I think I can show you some of the slides that we have tested at the time for 6 months, and was quite successful. Right now, SMBL is quite popular in many parts of the world, of course, and in Korea, this was very important project because Korea is a very small country, very highly populated, and during the time, I think we had a lot of needs to clean up the wastewater treatments. But if we can develop these SMBL systems, we can put those membrane system underground, okay, put it into underground, and you can use your the upper ground anyway. So that was very nice, and every single golf courses, there are some clubhouse. There is a small shops in between the golf courses, and they should be cleaned, and they were very concerned about the environment. Okay? So they have to use these SMBL units here in Korea, of course in Japan and other countries as well. So this was a very important initiating project. We just initiated, and now a lot of our graduates were happy to have the companies, and Pure Ambitech and many other companies are using this SMBL units and techniques, and so they're quite successful these days. Okay, this is the slide showing the gas treatment, natural gas treatment units. You see this kind of platforms. This is what we call the platform, and this platform will take the gas, natural gas from the gas well, and And the units, membrane units, these tubes, looks like a big tube, huge tubes. All of these tubes are membrane units. Okay? This membrane units, although it looks like a small one, you see this is the size of man, size of the human being. Okay? So this is a huge membrane module, and you have a picture here. Looks like it's a huge membrane module here. This is the spider one. Spider one module, also the spider one module. This is the hollow fiber membrane module. So hollow fiber membrane module might be smaller than the huge spider one modules. Usually the area to volume ratio for hollow fiber versus the spider one module is about 1 to 20. So the spider one module is about 20 times needs more 20 times the space than the hollow fiber membrane modules. These days, spider one modules are installed in many of the natural gas treatment factories or platforms. The cost of building this platform is about $200 million to about $500 million per platform, and it's a huge plant. So although in Korea we have so far built a lot of ships or the small engineering plants, but we are very keen to develop the platforms, not installing inside of the Korean peninsula, but of course in the many of the sites in the world, including the Middle East. And the engineering companies in Korea are very keen to have this project containing the membranes. So several companies are interested in, and even the Korean government, particularly the MOTI, Ministry of Trade and Industry and Economies, or something like that. They're putting a lot of money on developing this type of platforms from the Korean side. Now I'm showing you the two membrane units here. This is the Sayonara membrane units. These units are operated by the NATCO Chemical Company, NATCO Group, and they were very keen to use the hollow fiber membrane units. Okay? Hollow fiber membrane units from Doyobo Company. And Doyobo produces the cellulose acetate hollow fiber membrane modules for gas treatment, gas separation treatment. The UOP units here, UOP units, they also use the CO2 separation membrane systems, but this is the cellulose acetate fraction membrane units. So you see, UOP uses the huge, membrane modules, whereas NATCO uses the smaller module from the same materials. Now, I have explained to you about the OBIC systems already. So in summary, every single airplane units have to be equipped with the nitrogen inerting system called the OBIC system when they are flying, in the U.S. continent. So this is a big industry for the membrane producer, including the Monsanto or Air Products. Now, in order to separate these membrane units, what happened? Membrane units, usually the oxygen and nitrogens have a very small in number of difference in size, and if you wanted to separate the CO2 from methane, yes, we have about 0.5 Armstrong difference. If you're talking about the flue gas, flue gas from the power plant. Usually it contains about 10% to 15% of CO2, and rest of them are usually nitrogen. But the size between the CO2 and nitrogen is about 10%. But CO2 nitrogen separation is easier than oxygen nitrogen separation, because you think about the size of the oxygen and CO2. If you want to separate the hydrogen from methane or hydrogen from nitrogen, yes, it's much easier. Okay, you can separate the you can take the hydrogen because it's much smaller in size. So the size of gas molecules, particularly in this 3 to about 4 Armstrong level, is not that much, but in order to have a high flux, high separation membranes, the cavity size, or the what we call these microcavities or sub-nano size channel is very important. So let's assume that we have a membrane with a 2.8 Armstrong pore or channel. Okay, if I have a 2.8 Armstrong the channel, if I wanted to separate the hydrogen and maybe nitrogen or whatever, then I have to pressurize, pretty high in pressure because most of the gas molecules are pretty larger than the pore size. So I have to pressurize them. But if I have a little bit of a larger cavity size than 3.8 Armstrong, such as 3.5 or 3.8 Armstrong, yes, I can separate them without any high pressure. So this is the principle of the importance of the cavity sizes. And you see, we have to have Goldilocks cavities in this case. So we found some of the membrane called the TL membrane with a little bit of larger cavity sizes to separate these small gas molecules. And this was the first, the extensive article appeared in 2007 in collaboration with group in UT Austin and CSIRO in Australia. So what we have done was that we were working. We have developed some type of polymer material called TL material, and we tested this material. Of course, we plotted it here, and you see this is the upper bound. You saw the yellow line in the previous slide, and this is the red line here. But above this red line, this number represents our material developed in our laboratory, and you see all of these materials were above this upper bound, and these typical the glass polymers such as polyethylene terephthalate, polysulfone, polyphenylene sulfide, all of them were below this upper bound, and we can extend that this is the significant advance in material, and the reason why we have this high permeability and high selectivity is due to the cavity sizes. Cavity size for this molecule, after we treat this membrane from low temperature to high temperature, we can have a change in the size of the cavities versus the number of those cavities in y-axis. So the polyimide usually has 2.8 Armstrong in cavity size, whereas if a TL membrane has a larger cavity size ranging from up to about 3.5, 3.6 Armstrong, and the number is pretty high in that case. So this was accepted in this sense. Okay, so in gas separation membranes, usually the sorption and diffusion is very important aspect, because although we have 3.0 Armstrong in size of the cavities, usually those size is very small, so that sorption, diffusion, and desorption. sorption, diffusion, and desorption is very important mechanism for this the gas molecule transport. If I have a little bit of larger cavity sizes, if I have a little bigger sizes like a 4 ohm strong, 5 ohm strong, stuff like that, then usually we can separate this by the molecular sieving aspect without applying the high pressure. But if I have a little bit larger cavity sizes, larger pores than molecular sieving cases, then usually we can say that we have a surface diffusion, and in that case, a carbon membrane, zeolite membrane, or glass membrane are falling into this molecular sieving versus a surface diffusion, depending on the shape of the cavity and the size of the cavities or the free volumes. So these are a little bit of ambiguous in terms of the categories of these two. I put this slide because the CO2 separation is very important. Okay? Before this class, I'm teaching the energy environmental technology, and that is focusing on how we can battle with the CO2 or greenhouse gas issues in terms of energy production, in terms of our climate changes, and so on. And in that case, we wanted to, because we are talking about the membrane here, I'm putting this slide because CO2 recovery, CO2 emission problem is a big issue, but we have to recover. We have to, capture the CO2, and perhaps we can reuse, or we can store those CO2 back to the underground. Is a big issue these days. And if you're seeing this electrical power generation plant, perhaps from the coals or from natural gas, in the world, there is a statistics that we have about 5,000 coal-fired power plants, and that generates the 10 billion tons of CO2 per year. And so that you can calculate how many tons of CO2 there is generating from one single coal-fired power plant. And from the chimney, you see a lot of those water vapor along with the CO2 as well. The CO2 concentration here from the coal-fired power plant is about 15% usually, and 83% nitrogen, and the rest of them are water. Okay, and they have about absolute the pressure is about 0.3 bar, and the temperature is ranging from 50 to about 70 degrees C, okay, depending on the size as well. So the post-combustion CO2 recovery from the flue gas is very important, and so these days we're battling with pre-combustion CO2 recovery because the CO2 is coming from this chimney after generating the electricity, but pre-combustion is the one that we do not want it to emit the CO2 here, but rather we have to capture the CO2 during or before the generation of the CO2. So anyway, these are the two important processes. Perhaps we may have a time to talk about this more in detail later on. So this is the post-combustion. You see the size of these gas molecules are a little larger. The pre-combustion cases, we are battling with hydrogen and CO2. Post-combustion case, we are dealing with the CO2 and nitrogen. Of course, we have a different temperature, different pressure, different concentration between the two processes, of course. Okay, so we will talk about this in more detail later on in our gas separation process. But so far, this is all about the history about membrane and brief introduction of the membrane processes for RO and also in gas separations. Any questions so far about the history? BB? No? Understandable? Okay, so let's close the first chapter, then we can continue on the second chapter, chapter 2, on membrane preparation. Yes. So far, I think we have briefly talked about what about membrane? What is the membrane shape and what are the structures and so on. But we will talk about in more details, more specifics. Well, membrane can be defined that can separate the mixtures in the feed side to the permeate side. Okay? Now we have a mixture here in the first phase, and perhaps a single or the selected components in the permeate side. Phase might be different. Phase might be the same or different. Okay, phase might be gas phase of each, or liquid to liquid, or liquid to gas, or gas to liquid, whatever. So the phase might be changing. If your phase is changing, then you need more energy. Okay? But if you are dealing with the same phase, yes, we can have we can deal with the separation using these membranes. So most important part of this whole separation process is the membrane itself. So membrane material 2.0, material 3.0, material itself is very important. Membrane material and geometry is also important too, to achieve your the separation properties. So membrane may have a different structure, different function, different transfer property mechanisms because of the structures and geometries, and you can construct this membrane in different the functions. So membrane, although could be very beneficial to separate the mixtures, again, I wanted to emphasize that membrane may not be the ultimate, your ultimate goal or ultimate the application, because you may have other processes if you're dealing with the separations. Now we have talked about the dense membrane without any pores. This dense membrane can separate the mixtures using the solution diffusion mechanisms. So different membrane structure may have different mechanisms of separations. We have a porous membrane so that you can make the microfiltration, ultrafiltration membranes. If I have ions, we can have ion exchange membranes. Electrodialysis, reverse electrodialysis, and so on. If I have a hollow fiber membrane or microporous microporous membrane filled with the liquids, so that the liquids are not the mobile anymore in macroscopic terms, then this is what we call the supported liquid membranes. Because solid support membrane supports the liquids as well. I can have a symmetric membrane or anisotropic membrane in combining the phase separation made of one molecule, one polymer, or made of two polymers. Right? So I can have a composite membrane or asymmetric membrane in this case. We can have various types of geometries of the membranes, ranging from flash type of membrane. This is the picture of SMBL, submerged type membrane bioreactor. This is plastic case, and the white part is a membrane, flash membrane, like a paper, and you have two membranes, in one module. But in between these two modules, we have a perforated plastics, so that we pull the vacuum here, so that the water is going to inside of this, through this membrane and inside to the membrane, so that this clean water will be collected from here. So SMBL uses the vacuum pump to pull the clean water. Hollow fiber membrane system has smaller in size, usually less than 1 millimeter or 10,000 micrometer. Tubular membrane is ranging from 2 to several millimeter. So I think this is the error. So several millimeter in tubes and so on. I think I have to stop. I wanted to stop here because they wanted to take the gradation, the picture for the gradates. It's scheduled at 11:30, so I wanted to stop a little bit earlier, 15 minutes earlier here today. So from now on, I think we can discuss later on Friday about the membrane processes, membrane materials, how we can make polymers, how we can make what are the important properties of polymers, what are the important parameters governing the membrane preparation, stuff like that. We will talk about the phase separation. We will talk about the thermodynamics, spinodal decomposition, bimodal decomposition, stuff like that, on Friday. Okay, so thank you, and we'll see you on Friday.